Buenas tardes,
Hello.
estamos aquí en el segundo día de Figap Digital Expo en live y le damos bienvenida a John Byrne, que será quien nos presente el último webinar del día de hoy, que en esta ocasión les mencionamos que será el live solamente en inglés, pero les recordamos que pueden ver esta y las presentaciones anteriores en nuestras redes sociales y en nuestra página www.figap.com. Posteriormente, esta tendrá los subtítulos en español para que la puedan disfrutar de la mejor manera. Welcome, John.
Thank you. Thanks for having me. Buenas tardes. Gracias por venir. And that'll be the limit of my Spanish. It'll all go in English. Thank you for coming. I greatly appreciate it. Let's get started.
Yes.
Let's go to that first slide next, please. Okay. I work for Leidig Systems, Inc. as an international sales manager. I've been with them for 40 years, just short of 40 years. So I've seen a lot of different applications. But today, I'd like to talk about solutions for silo bridging. And that's what this discussion will be about. It's about 30 minutes long, and it'll be about 10 to 15 minutes worth of questions. Next slide, please. Yes, we're going to start with this. This is very interesting. How many facilities have you gone to where you see the hammer track marks on these hoppers? All over the world. I've seen them in India and Mexico and Argentina, Brazil. It's kind of a funny picture, but not really if you have to live with that. Now you look at the site on the right, that's obviously somebody has an upset condition. That meal is standing vertically. Unreal, you would think. Well, let's discuss how we can prevent this from happening. Next slide, please. With large storage capacity, it always begins with flow. This graphic talks about the silos where you have these different colors. Red is non-free-flowing, it's static. Yellow, that is semi-flowing, and green is flowing. Typically, this is what you see in a funnel flow silo. Next slide, please. As time passes, you're going to get some things going on in that silo, primarily driven by moisture. That material, meal, bran, those sort of things will compact when stacked in a vertical silo. They'll densify. That material will be very cohesive. All the things are bad if you don't design for that in a properly designed silo. Next slide, please. Okay, this is a typical picture here on the left. That is what a result of channel flow. Channel flow is when, in the right-hand side graphic, you see the red static material has gotten larger. The flow channel down through the middle has gotten smaller. So when you have that situation, eventually that donut-looking material that you see on the left is going to grow bigger and bigger. And eventually, it'll cause a bridge. But besides that, that material is static. We're dealing with an organic material with a higher moisture content. That's the infestation point. Now, depending on your process, that's probably going to be bad. Let's move to the next slide, please. Here, this is the result, rat holing. See the red graphic on the right in the silo? The red portion has gotten even larger. The yellow's smaller and the green is very small. Well, eventually that's going to bridge over. You have your infestation point, it's getting larger. Your flow channel is getting smaller. And really, if you look at it, if that silo has a unit volume of 10, you're effectively using 1 or 2, not to mention creating a problem for infestation or quality. Next slide, please. This guy, he was so upset with his channel flow that ended up in bridging that he cut a hole in the side of that silo. So that channel down through the middle, as you can see on the right, is no longer there. The material got to a point where the hole is small enough that it could gather enough strength. This material could gather enough strength and become a bridge. Now you're stuck. Now what do? This guy, if you look at the bottom of that cone outlet, there's a flange. This application was with a vibratory bin bottom. Now, later on in this discussion, we're going to be going through a number of different, what should I say, technology to empty silos, the pros and the cons. But now we're just going to discuss how we can design for a silo and design it correctly. So we have a number of questions. So we're going to go through that next. Next slide, please. Here, some results. Poor material flow, process interruptions, sledgehammers. You know, it's kind of, again, a funny picture, but you can see this, they've been living with this problem, left-hand slides or pictures, for a number of time, a long period of time. So the guy with the sledgehammer, he hits it, that transition, that vibratory bin bottom, as that picture, that's actually causing a problem because you're indenting the steel more and more, even reducing the area that the material has to flow through. Just a huge problem. Nobody should own a sledgehammer, that's for sure. Let's move to the next slide, please. Okay. When you have bridging problems, channel flow, eventually some of those bridges will fail, causing implosion. As you can see in the picture on the left, that's silo roof failure. That's due to an implosion. A bridge was formed, it collapsed. The silo did not have enough strength in the roof or ventilation in the roof to accommodate the sudden inrush of air that's needed when you have an implosion. The secondary thing is, if the roof works, you could get a silo failure like the silo on the right. It's actually high moisture corn. And that corn was channel flowing, and eventually the bridge fell at the weak seam, which is the transition from the bottom to the top of the silo, failed and it fell over. So we're going to try to avoid that with a good set of questions and good designs. Let's go to the next slide, please. Okay, how do we avoid these situations? The hammer marks or hammer track marks on the hopper or implosions on the right. You can see that hopper not only had a hammer on the left, lots of them, but also local vibration on the steel pad in the lower center. That was a local vibration pad. That didn't work either. So let's try to avoid these situations. Let's continue. Next slide, please. Okay, people look at this stuff, meals, DDGSs, canola meal, soybean meal, and they put it in their hand and say, wow, such an innocent product. How can that be a problem? It can be a problem if you don't design correctly. So we deal with a lot of DDGSs, a lot of canola meal, tremendous amount of soybean meal. All has varying moisture contents, varying oil contents, protein contents. All those things affect flow that affect design. Next slide, please. Okay, material considerations. Material to be stored. Is it wheat bran? Is it soybean meal? Is it canola meal? Sunflower meal? What is it? Identify that. What is the temperature going into the storage? In other words, for instance, at a DDGS facility or even a soybean extraction facility, you're going to be above ambient with the material going into the silo. Okay. Once you transload that through a rail car or something, let's say you take it from the Midwest of the US and bring it to Mexico, that temperature is dissipated. So it's going to be easier to handle at a feed mill than it would be at an oilseed extractor. How much does this product compress? You have in your hand, you say, wow, this bran weighs 250 kgs per meter cubed. That's true. But when you stack in the silo with a 2.5 to 1 height to diameter ratio, it will compress to in excess of 641 kgs per meter cubed. That affects flow. So you have to evaluate the product, just how much compressibility you have. Particle size matters. We need to know the particle size. The bigger the particle size, the more it's going to be able to compress and bridge. The size of the particles is very important. Density is important because we have to have the silo designed properly, the cone designed properly, and the reclaim device, whatever it is, needs to be designed for that density as well. Retention time, that's an important issue. We'll discuss that further. Retention time, in my mind, says, okay, if we have long retention times, we need to design for recycle. Then obviously, every application has to have a discharge rate, what we call a discharge rate. How many tons per hour, cubic meters per minute do we need coming from the silo to the truck, to the bagger, to a process? That needs to be identified. Next slide, please. Okay, reclaim system considerations. We'll always ask these questions. They're important. Percent of moisture, will it vary? Particle size, will it vary? Bulk density, loose and compressed, we talked about that earlier. Duty cycle, are we going to run 1 hour a day, 8 hours a day, or 24/7? That duty cycle needs to be identified as well. Recycle capabilities. Everybody thinks about, okay, we need 1,000 tons. That's great. And it's going to be working 8 hours a day. That's great. But for instance, in Mexico with Pascua, Easter, or Navidad, Christmas, or Fin de Año, those type of long weekends, no truck traffic, no process running, we need to have recycle capabilities, especially if the silo is above 50% full. Next slide, please. Okay, silo design concepts. Here's the first one. Funnel flow design. It's used with free-flowing materials like grains. First in, last out normally because it's free-flowing down through the center. And you have consistent load on the silo sidewalls. That's basically the funnel flow design. Next slide, please. Mass flow. In this situation, you're using it with non-free-flowing materials like brands and meals. You really would love to get first in, first out, and you're going to have some dynamic loads. What does this mass flow mean? It's one to flow in mass. So you're going to have more drag on the silo sidewalls. So your silo has to be designed for it, to take that stress. You're going to have a cone bottom at the bottom. You're going to have some loads that are going into that cone in mass, like a piston, if you will. And you're going to have some dynamic loading. We'll describe dynamic loading next. Next slide, please. Silo design concepts. Side loading, meaning you're coming out of the side of the silo. Upset conditions. If you have an upset condition with the brand silo, you're going to get some side loading that we need to address for in the design up front. Safety and structural integrity. That's all about side loading. You need to design for side loading with these hard-to-flow products. Next slide, please. Here's the dynamic loading slide. Here, if you're using some sort of radial reclaimer with an auger that sweeps around the bottom of the silo, whether it's flat or on a cone, doesn't matter. What you have is in front of that auger that's conveying material to the center, there's going to be a pressure on the wall. It's going to push out. Now, behind that auger, it wants to pull in because there's less material or fluid material. So that's an S pattern, okay? You have to design for that in your structural calcs for these silo sidewalls. As it moves forward and around, that S pattern follows the auger. So it's dynamic. You're moving around and around all the time. So you have to design for dynamic loading. Next slide, please. Height to diameter ratios. This is important and is not addressed enough. The silo on the right, maybe 15 feet wide, 20 feet wide, 100 feet tall, 6:7 to 1 height to diameter ratio. That material, if you put a dry bulk material in that silo, like a brand, you're going to get enough drag on the silo sidewall, compression, that you're going to bridge wall to wall above whatever reclaim device you have in the bottom. So height to diameter ratio is important. For instance, soybean meal, oilseed extractor, hot meal, 10 degrees over ambient. You're going to want to have something like a 2.5 to 1 height to diameter ratio, no more. That same meal, once you move it from South Dakota to Guadalajara, that heat is dissipated, it's gone. You've transloaded, You can take that same meal and put it at a feed plant and add a 3-to-1 height to diameter ratio. So let's make a little bit more comparisons here. We do a lot of work in the wood industry. You get sander dust, very fine, dry. 3-4-to-1 height to diameter ratio will work well. Sawdust, 3-to-1. Shavings, 2-to-1. Wood chips, 2-to-1. Bark, big ugly bark, 1-to-1. So the bigger the particle size, the wider the geometry of the application. Next slide, please. Okay, goals for soybean meal and bran silos, bran or mints. Wouldn't it be nice to have FIFO, first in, first out? Primera entrada, primera salida. A little Castellano for you. No hard pack left in the silo, meaning that you clean out your silo. You don't have those infestation points. No bridging or puentes. You get rid of that. Wouldn't it be nice to have that? A controlled flow. In other words, when you turn the machine on, you get your 20 tons an hour all the way through until your silo's almost empty. Obviously, then the flow rate drops off. Quality control. If you know you're getting first in, first out, you have less fear about downstream quality issues with your client. Wouldn't it be nice to have easy maintenance of whatever reclaimed device you put in the silo? So maintenance is a lot of times overlooked, but these silos are built for 20, 30, 40 years of operations. So as the architects of these silos up front, let's think about that maintenance guy that's turning the wrench. Next slide, please. Now we're going to talk about various designs of how we can extract this material from storage silos. We're going to talk about air cannons, vibratory ridden bottoms, live bottoms, poles with chains, and radial screw type. All those things have places in the industry, but if you're storing meals in silos, we have to be careful on how we do this. Next slide. Air cannons. You can see that's a compressed air pod there. They have a number of them there on those silos. So let's talk about that. It's not true live bottom. You're just localizing air in the product, trying to get this thing to break up and flow. It's not 100% cross-sectional activation. You don't understand that phrase yet, but we're going to develop that phrase. Relies on local blast of air to break apart the material and move the product. It creates channel flow, and it's not FIFO, so you have a quality issue as well. The larger the silo, the more problematic this design becomes. So let's go to the next slide, please. You can see here, you have an air compressor, that's the blue tank. You're running it up to some nozzles. You're shooting air in there, trying to get this material to flow. Now, air cannons do have their place. Small silos or non-organic materials, or in transitions like you see here. So they do have their place. But if you're running a storage silo, more than 50 tons to 1,000 tons, you might not want to use air cannons. They're just not exactly right for the application. Next slide, please. Vibratory bin bottoms. You see a tremendous amount of these out in the field. Okay? Again, it's not a live bottom. Doesn't have 100% cross-sectional activation. Relies on vibration to move the product. The ability to flow with varying inputs affects the performance of this machine. So what is varying inputs? Varying inputs, if your moisture moves, if your particle size moves, and if your flow rate changes. These devices, not so much. Creates channel flow. It's not FIFO. So again, in these organic materials like bran and meals, you're going to get channel flow and not FIFO. That quality issue comes back into the operator's mind. The larger the silo, the more problematic this vibratory rim bottom device becomes. Next slide, please. You can see here the picture on the left and the graphic on the right. It's a vibratory bend bottom. You have the gyration motor hanging off to the side of that, makes that cone vibrate. You're trying to get to flow. But you see in the graphic on the right, they have this little TP looking thing, the little cone in the middle. That is restricting flow. They need that for the machine to work. But it also is a positive slope that allows material to bridge off of it. So you could get a double Roman arch off of that. So again, they have their place in the industry. Fine product, very repeatable particle size, moisture contents that are low. And normally you see these things successful in inorganic materials like limes, things like that. Next slide, please. Live bottom systems. I love talking about this because you see a tremendous amount of these out in the field as well. Again, it's not a live bottom, it's not a true live bottom. 100% cross-sectional activation. Well, that machine is bolted to the bottom of a truncated cone. So you still have a positive slope. You're not undercutting the whole mass of the material of the silo, just that truncated cone outlet. So creates a hard pack at the point where the screw goes through the opening pinch point. The next slide will develop that comment a little more. High wear at that pinch point. Lots of connected horsepower to get those screws to move. You're actually making the screws a bunch of extruders, if you will, high horsepower requirement. Creates channel flow. They normally feed from the back end of that auger, and that's channel flow, and it's not FIFO. So with those comments, let's go to the next slide to develop them a little more. Next slide, please. Okay. As you can see here in this live bottom material flow issues, you have the initial flow on the left, restricted flow in the middle, and bridged on the right. The initial flow is everything's running well. You're flowing, you get some static reds on the cone hoppers, if you will. Then starts building up because you're feeding from the tail end of this thing. Now, yes, you're going to have variable pitch flighting, variable diameter, and that sort of thing. But for some reason, you cannot get this to come down evenly on these screws. Now, as you convey from left to right, you see the pinch point there. That pinch point becomes high wear, high horsepower, and it also creates a hard pack that will grow over time and eventually give you a bridge. So again, these have places in the marketplace, not with storage silos of large volumes of, let's say, 200, 300, 400 tons, normally much smaller than that, to get them to operate correctly. Okay, next slide, please. This one, this is a pole with chains. Sometimes it's called a Flying Dutchman. It's inexpensive, that is true, but doesn't give you 100% cross-sectional activation, so you still have that infestation concern. These cutting chains do not extend to the silo sidewall due to product compression. So you see the pipe on the right with the guide in this silo trying to maintain this thing. That pipe is going to spin about 70 RPM. That centrifugal force with the cutter at the end of that chain is going to want to extend out to the wall. But with this compressed product, it'll never get there. So you're just going to have this large donut, and an infestation becomes a concern. Creates hard pack at the silo sidewall where the cone comes into play. Safety for maintenance, it's a disaster. Channel flow for sure. Again, that's a quality issue, and it's not FIFO. So with all those data points out there, let's look at the graphic. Next slide, please. Okay, you can see the graphic on the right. The pole is the vertical part. The chains are swinging outwards. The pole runs about 60, 70 RPMs. The goal is to get those chains to fly all the way out to the edge. They don't do that, especially with silos that are 4 or 5 meters and up and have a 2 or 3 height to diameter ratio, 2 or 3 to 1 height to diameter ratio. Those chains will never get out there. So that donut will be developed, like I showed you on an earlier slide. You have an infestation concern, you eventually are going to have a product bridge up in that area. Then if that bridge were to fall, what happens? It falls down on that pipe. The pipe it's bent. Now it starts to wobble. The bearings start to wear. You have a maintenance issue. So again, they have their place, but not in large storage vessels of more than 400 tons. Okay, next slide, please. Angle hoppers. Okay, this is equipment that's based on a design study per given sample. So this is how it works. I get a sample from you. I do some calculations. I do some tests. Based on this sample, I'm going to give you some recommendations on angles, etc. That's what this client with this vendor would do. Okay, so now it must be redesigned if the product varies in moisture, bulk density, or particle size. So what does that mean? If you have if your inputs are varying, moisture, particle size, flow rate, or height of product, because it's compressing, you may have to redesign that thing. So it has its place, but you got to be careful with it. Negative to it, large vertical space for it to be able to fit in a silo. That's lost storage. So there's some practical matters there too. Extreme vertical height. It's not 100% cross-sectional activation, creates channel flow, and it's not FIFO. Now, do they have their place? Yeah, they do have their place. The place would be inorganic materials, very repeatable inputs, moisture, particle size particularly. They'll work. But if you have a varying moisture, varying particle size, or varying heights, you got to be careful. Next slide, please. Okay, now we're going to discuss radio auger designs. For instance, here, this auger in the center picture, it's going to be running parallel to the cone slope. The tip of that auger is going to be within centimeters of the silo wall, conveying away from the silo wall, conveying down that slope, not riding on the cone, conveying parallel to the cone. And it advances around the bottom of the silo. That's going to give you 100% cross-sectional activation. Because it has a hydraulic rotary union, the product falls through the union, it's a hollow bore, you're going to go round and round all the time. So you don't have to windshield wiper. So you're really going to get 100% cross-sectional activation. You can see in the right-hand picture how easy all those maintenance points are. Those maintenance points are exterior of the product zone. Super important. You see that as well on the left, excuse me. The left side, you also see the hydraulic rotary union, that's hollow bore, that allows the product to fall through down into the takeaway conveyor device. So that's a radio auger design. Next slide, please. Okay, here you have it in a cone bottom. This cone bottom machine for lighting will go up to 18 meters diameter. And it'll handle product up to about 3/4 inch diameter in some dry woods. But in meals, this is an excellent machine to handle meals. All the maintenance points are exterior, 100% cross-sectional activation. It's just a wonderful application, or a wonderful machine for these type of applications. Next slide, please. So, cone bottom material flow fears. These are the fears all investors have. I'm going to have free flow, left graphic. I'm going to have some restricted flow. God, I'm going to get some rattling. Hey, if I get bridging, what do I do? That is a common fear that we need to address as people applying equipment. We're the architect. We got to do this right for the client because those silos will be there. I have silos in Mexico that I put in 1994. They're still operating. So let's do it right up front. Next slide, please. Okay, cone bottom benefits. This machine is going to give you fast load out, no product segregation. It's going to give you first in, first out. It's going to eliminate bridging, total clean out, no downtime or less downtime, no infestation. That's the biggest part. No infestation, no downstream client complaints, no degradation of the product. Your silo, because you're going to mass flow it, is going to have improved silo life. No clean out charges, you eliminate them. Confined space becoming a big issue. All maintenance points, exterior of the product zone, confined space goes away, or at least the concern of confined space goes away. State-of-the-art engineering. So that's typically what that lading and loader is in a cone bottom. Next slide, please. Okay, operational procedures. Operate the reclaim system during the filling process. So when you're filling, now you guys in Mexico, a lot of times you'll get unit trains that come in and you want to fill it from the ground up. That's true. But every 10 or 20 feet of that silo, turn this machine on, let it run for 10, 15 seconds. Now, daily use, feeding trucks, if you're a reseller, bagging systems, recycle, if you're a feed mill, you're using it. Okay, that's great. But on long weekends, when your plant's not running and the silo's full, let's design in recycle. Recycle is very important, especially when that silo is half full or more. Now, recycle could be filling the bagger, filling the pellet line, filling a truck, or just recycling back into the silo. Design that into your system. You'll be glad to do that. Next slide, please. Machine interface. This is a computer, basically, Siemens or Allen Bradley. So this has become more and more important, especially during COVID. I've had our technicians go into sites in Mexico, start up multiple machines remotely. So with this, what we call LMI, you have Ethernet interface. You can access that remotely, okay? That means you can troubleshoot. We can see the trending on what's going on that silo. So it's really a good diagnostic machine. Now, I gotta tell you a story. When this first came out, I wasn't sold on it. I thought, no way. I've been doing this a long time, no way. But I was proven wrong. With this machine, this LMI, you're running that machine to a greater level. That means your available on time is much greater, and my warranty costs go down. Now you say warranty costs go down, that's your problem. But my warranty costs go down because of proper operations. Your available on time goes up. You're going to have a more profitable line. So this LMI has proven itself very effective, a very good thing to put in. And I had to be, what's the old phrase, show me type of thing. And I was showing, and I'm a fan now. Okay, next slide. I wanted to talk about a retrofit. This is retrofit in Eastern US. I'm going to use the word Delaware, but I don't know. The picture on the left is the existing silo and cone. You can see the white cone and then the truncated cone, and then there's a live bottom on the bottom of that. Well, these guys put it in, fought it for a few years, and they said, this is not good. So what we did, we took out the brown truncated cone, took out the 65-degree cone. You can see some crinkles on that cone. They've already had some failures going on there, bridging and closing. We took that all out. Then we put in a new cone. We bolted it into the same position where the old cone bolted to the vertical sidewall. Put in a 30-degree cone, bolted in our machine. That created a lot of space, shot a transition down to the existing takeaway conveyor, and there it is. Now they have a silo that's working for them. As you can see, the picture on the right shows you how easy that access is. That's on top of that mezzanine level that you see in the middle picture. So that's just one way Lady can solve existing flow problems in your silos. Next slide, please. Conclusions. Manufacturers' experience is important. Multiple distinct industries. We serve 9 distinct industries. That means we're getting a lot of cross-pollination from one industry to another. That comes back to a central engineering that then can affect silo design. So that experience is so invaluable. We draw upon thousands of applications around the world that help design the next series of machines. And I was taught this by a good, actually a Cargill guy. He said, John, that first dollar we spend, that's the cheapest dollar. What does that mean? Retrofits are expensive. Let's do it right the first time through. Next slide, please. I like to end on this slide. Why? Because I work for a company that's a family company. I work for 3 generations. Now, the collage of pictures is like this. That's the first Leydig unloader, upper left-hand corner. Center, that's John Leydig, the founder. He's gone now. But that's his first unloader on the left. Now, on the right, that's his son, Win Leydig, second generation. So you can see from left to right, we got 2 generations here. But then it continues on, lower left, there's Daniel Leydig. So we have 3 generations. And on the right, we have the latest and greatest cone bottom machines. They go up to 18 meters diameter. So we're a family-owned company. It's been a seamless generational change of ownership that I'm proud to work for, and hopefully you've gained something from our little webinar here. Next slide, please. I want to say thank you for joining this webinar, and if you have any questions, feel free. Okay, if there's no questions, I guess we can move on.
Thank you so much, John, for sharing.
You're welcome. Thank you for the opportunity.
You're welcome.
Okay.
Le recordamos a toda nuestra audiencia que esta conferencia, este webinar, lo encontrarán más adelante ya con subtítulos, por si no les quedó algo tan claro. Y de igual manera pueden pasar a la zona roja, al stand virtual de Leydig, a hacerles preguntas directamente tanto a John como a sus colegas. Muchísimas gracias por compartir este espacio con nosotros, por estar presentes en Figap Digital Expo en Live por primera vez, y los esperamos el día de mañana. Tenemos más webinars también a partir de las 10 de la mañana. Muchísimas gracias, buena tarde.
Okay.